Good day, everyone. This is Jim Hazard, 3DEC Product Manager, and I'm going to give a brief introduction to 3DEC, which is the software that will be used in the subsequent webinar. So if you haven't heard of it before, or if you haven't seen it before, 3DEC is a numerical modeling program developed by ITASCA, and it's used to simulate an assembly of blocks stuck together. And so what it allows you to do is simulate anything from perhaps something more like a continuum on the left-hand side here with a bunch of faults or joints in it, all the way through to something which is completely discontinuous and a bunch of pieces are moving relative to each other. Now we call this a hybrid approach because the individual pieces can move relative to each other, but the individual pieces can also deform and fail like little continuum models. So the discontinuities are simulated using the distinct element method so that we can look at the shear movement and separation and so on between the pieces. The pieces themselves may be deformable, and we use the finite volume formulation to calculate the displacements and stresses in the individual pieces. And this is the exact same approach that is used by FLAC and FLAC3D. Finally, we use the explicit solution scheme to do the calculations. And what this means is that it does the calculations by marching forward in time rather than doing a big matrix inversion. And we do this approach because it's useful for things that are highly nonlinear. So if you have something that's dynamic, something with large strain, something with sort of nonlinear material behavior, this is a fairly robust way to reach the solution. And it works well for a program like 3DEC, where you do have a lot of nonlinearities. Now, 3DEC has a lot of interesting features, and I certainly won't talk about them all. But there are a few things I should just highlight before we get into the webinar, because these are the things that you will see in a moment. Number one is that we have the ability to create discrete fracture networks. So you can specify a size distribution, a position distribution, and an orientation distribution, and generate a network of fractures. Often it's a bunch of disks, like I'm showing here on the left. And once you have that fracture network, you can use them to cut into a 3DEC model and create a bunch of blocks. And again, these blocks are then capable of moving relative to each other. The second feature is fluid flow. So once you have a model with some joints in it, you can simulate fluid flow along the joints, and you can also simulate fluid flow between the joints. It's fully coupled, so meaning that the pore pressures can potentially cause the blocks to move, and the moving blocks can potentially cause changes in aperture, which changes the rate of flow in the joints. So you have this two-way fluid mechanical coupling. And if you haven't seen it, fairly recently, we've added the implicit solution scheme for joints so that the joint flow calculation now goes significantly faster than it used to. And then the last thing I'll talk about is dynamics. Like I said, the explicit solution scheme is very appropriate for modeling dynamic simulation. So often people use this for looking at the effect of earthquakes or maybe some sort of explosion like I'm showing here. And then you can look at the effects of the propagating waves on joint movement or failure or something like that. And so these are things that will be used in the upcoming webinar. And so that's all from me. I'm going to pass it over to Bruno. Thank you.
Hello, everyone. This presentation entitles Discrete Fracture Network Modeling Framework to Study Sensitivity of Fracture Transmissivity under Seismic Triggering. This presentation focuses on the project hydromechanical response of the fracture rock mass under seismic triggering. The client is SQV, located in Sweden. The main object of the project is to improve the understanding of the fluid pressure diffusion into discrete fracture networks and potential changes in fracture transmissivity due to seismic triggering. The approach that was used includes discrete fracture network DFN modeling, subjected to seismic triggering under different degrees of hydromechanical coupling. I'm Bruno Figueiredo. I'm a geomechanical engineer and I'm based in the Swedish office. I have a degree in civil engineering and a master in structural engineering from the Higher Technical Institute of Lisbon in Portugal, and a PhD in geophysics from the Institut de Physique de Globe de Strasbourg in France. For more details about my career, you can consult my bio in the link provided. As you might know, seismic triggering can induce permanent increase or decrease in the water level in boreholes. Trigger seismic events of small magnitude can result in an increase of the fracture transmissivity and rock mass equivalent permeability. These changes in fracture transmissivity are a concern for SQV because they can create new pathways for radionuclide transport, and they need to be assessed for the safety design of the future repository at Forsmark, which will be located at an approximate depth of 500 meters. Forsmark is located north of Stockholm, Sweden, as you can see on the top right figure. The layout of the repository is shown on the bottom right figure. ITASCA improved the understanding of fluid pressure diffusion into fractured rocks subjected to seismic events and potential changes in fracture transmissivity. The acquired knowledge will be useful for the design of the repository at Forsmark. The main goals of the project are to study the role of the geometry of DFNs on changes in the fracture transmissivity due to seismic triggering, to improve the understanding of the fluid pressure diffusion into DFNs and potential changes in fracture transmissivity, to study the level of hydromechanical coupling between fluid flow and rock mechanics effects, to identify the key process that can induce significant variations of a fracture transmissivity. This project proved to be quite challenging as it combines modeling of discrete fracture networks, hydromechanical processes, and dynamic analysis of seismic events. Several simplifications and assumptions were made to decrease the computational time and to make the model more manageable numerically, such as model simplifications, for example, the simplified DFN geometry and zones size, and some model assumptions such as the hydraulic apertures during hydromechanical coupling, the relation between initial mechanical and hydraulic fracture aperture, and the water bulk models decreased by 10 times. High sensitivity of the results to key input parameters, such as the water bulk models, fracture stiffness, and the fracture aperture. And significant increase of the simulation time as the complexity of the DFN increases. ITASCA, with the collaboration of University of Rennes and CNRS, developed a discrete fracture network modeling framework to study sensitivity of fracture transmissivity under seismic triggering and interpreted the results. ITASCA has unique knowledge and expertise on modeling of DFNs, coupled hydromechanical process, and dynamic seismic events. To answer the overarching questions, ITASCA created simple DFN models with different degrees of fracture orientation and connectivity between the fractures, performed dynamic analysis of the seismic events where an oscillogram was applied at the bottom boundary of the 3-deck model, and perform hydromechanical coupling using two levels of coupling during the dynamic analysis, considering both undrained and drained conditions. Under drained conditions, fluid flow is active and coupled with rock mechanical effects. So in this degree of hydromechanical coupling, fluid pressure diffusion is considered. Under undrained conditions, there is no fluid flow. The deformation is not induced by diffusion-related fluid pressure changes, but by mechanical loading occurring on relatively short time scale. So such the fluid pressure diffusion can be neglected. So ITASCA developed and used custom scripts to export key results from 3DEC and present these in graphics. And also establish correlation between the various types of results. For example, variation of fluid pressure versus fracture area with new shear slip. The 3D discontinuum-based numerical model developed in 3DEC is shown on the left figure. The model includes 10 fractures with varied size and orientations. The oscillogram, shown on the right figure, includes the accelerations histories in 3 directions, 2 horizontal and 1 vertical, which are converted into variations as a function of time of the shear and normal stress components. These stress variations are applied at the bottom boundary of the model. The duration of the seismic event is 6 seconds. 2 DFNs with different fracture orientation and degrees of connectivity between the fractures were analyzed. The studied DFNs do not reproduce any particular area of Foch-Mark, but they were used to study the dominant hydromechanical process during the seismic event. A sensitivity analysis to the key input parameters, such as the initial fracture aperture and fracture stiffness, was conducted. So the input parameters are the rock mass properties, the cohesion, friction angle, dilation, unit weight, fracture stiffness, fracture aperture, the geometry of the DFN, the size and orientation of the fractures, the initial in situ stresses and fluid pressure at 500 meters depth, and the oscillogram. Several numerical simulations were conducted. 3DEC data files were created to accommodate a wide range of simulations with different hydromechanical conditions and input parameters. So stressed fluid pressure conditions at 500 meters depth were considered, and the model was run until initial equilibrium is reached. Dynamic analysis of the seismic event was conducted, and during the analysis, both drained and undrained conditions were considered. To post-process the results from numerical simulations, fish scripts were developed to export during the dynamic analysis values of key parameters. For example, the fracture aperture and the fluid pressure, and these values were exported to text files. Also, MATLAB scripts were developed to read the exported text files and to represent graphically the histories of the parameters and the relations between the various parameters. For example, effective normal stress versus fracture aperture, and the fluid pressure versus area of the new tensile opening and shear slip. During the seismic event, results from undrained and drained conditions were found to be very similar, which shows very little fluid pressure diffusion. diffusion. During the seismic events, the fracture aperture increases, as you can see in the top right figure, which results in a decrease in the initial fluid pressure, which in turn leads to an increase in the effective normal stress and less critical shear stress fractures, as you can see in the center right figure. In the center right figure, the color bar represents time. So initially, at 0 seconds, the fracture is critical shear stress. Shear stress is near the shear strength. But then, the effective stress increases as time increases. So the fracture becomes less shear stressed. Simulations were done without fluid pressure, which we call a dry run, and with several initial values for fluid pressure. It was found that fluid pressure increases the occurrence of critical shear stress fractures, which increases the aperture with shear dilation. It was found that shear slip and dilation is more prevalent than tensile opening and more significant at the beginning of the seismic event for critical shear stress fractures. Initial critical shear stress fractures get more triggered by the seismic events, as you can see in the bottom right figure. In the bottom right figure, in fracture 2, the percentage of total area with new shear slip it's approximately 30% at the beginning of the seismic event. Results were found to be quite sensitive to DFN geometry, water bulk models, dilation angle, fracture stiffness, and initial fracture aperture. Changes in the fluid pressure are directly correlated with areas with new shear slip. Fractures 2 and 10 are initially critical stressed. So shear stress is near the shear strength. And these fractures are dipping 30 degrees relatively to the horizontal plane. So these fractures are easily triggered by the seismic events at the beginning of the dynamic analysis, which results in a decay in the fluid pressure, as you can see in the right figure. In contrast, for fracture 8, the area of new shear slip is relatively small, as you can see in the left figure. So this fracture is less triggered by the seismic event. So the fluid pressure decay is much smaller than this in fractures 2 and 10, as you can see in the right figure. Now I'm going to talk about the results obtained after the seismic event. So at 6 seconds, the seismic event was stopped and the model was run under drain conditions. So the fluid flow process was assumed to be the master, while the mechanical process was assumed to be the slave. So the total time was assumed to be controlled by the fluid process. The fluid pressure variation with time is shown on the left figure, while the percentage of area of each fracture with new shear slip is shown on the right figure. The results show that after the seismic event is stopped at 6 seconds, the fluid pressure continues to vary because of fluid pressure diffusion. And that's 100 seconds, approximately 100 seconds, the fluid pressure in the various fractures is approximately the same. This result is because the flow connects all the fractures until a uniform hydraulic head is reached. The time necessary for fluid pressure diffusion is approximately 100 seconds, which is larger than the duration of the seismic event, which is 6 seconds. So this result explains the small diffusivity of the fluid pressure during the seismic triggering. The right figure shows that significant shear slip occurs mainly in the fractures dipping 30 degrees And this result enables to conclude that the diffusivity of the fluid pressure can reactivate other pre-existing fractures by shear and eventually induce other seismic events. So that's all. Thank you very much for your attendance.
First question. Could you please clarify the current extent of multi-physics coupling in 3DEC? Specifically, does 3DEC support fully coupled thermal hydromechanical simulations, including heat transfer, fluid flow, and stress deformation feedbacks? Or is the coupling limited to thermomechanical or hydromechanical domains?
Yes, you can do full thermal hydromechanical. Be aware that the thermal only works one way, so that the temperature changes will influence the expansion of the material and change the deformation, but it doesn't work backwards. The deformation doesn't change the thermal. I think that's probably okay. There is some sort of coupling between the fluid and the thermal. Some people use that for these nuclear waste type problems. So yeah, I guess the short answer is yes. You can do full thermal hydromechanical coupling with some provisos. Not every possible mechanism of interaction between these things is possible, but some of them definitely are. So,
and then a continuation of that question. Are there recommended workflows or software combinations, for example, 3DEC plus FLAC 3D or other external tools, to achieve fully coupled THM modeling in fractured rock masses?
I mean, 3DEC is going to be your best bet here. In FLAC 3D, there's no flow along the joints. So any of this kind of stuff you want to do, you're going to need 3DEC.
I would just add that you can couple 3DEC to FLAC 3D. So, but usually that's used if you wanted to have like a far field space around your fractured rock mass, just to get the stresses right. The other thing I might mention is that we have another software called X8. X8 is specifically designed for hydraulic fracturing, where you can have pre-existing joint sets, but also have new fracture initiation. And it also is fully coupled in terms of thermomechanical and hydromechanical domains, fluid flow along joints and so forth. So that might be something you would be interested in looking at further. On the last slide, after seismic event is gone, will there be new fractures generated?
No, it's the same fractures. But what happens is that when you stop the seismic event, there is a fluid pressure diffusion, and this can reactivate other fractures. So other areas of fractures slip, but no new fractures.
Great, thank you, Bruno. Next question. Does the Hook-Brown model in 3DEC allow for viscoplastic behavior and hardening softening? Or is it limited to elastic, perfectly plastic behavior?
I'll take that one. Hook-Brown does not have to be perfectly plastic. You can have hardening, you can have softening. 50% of that question we can do. It's already built in to allow hardening and softening. In terms of viscoplastic, assuming you mean like time-dependent creep type stuff, that is not built in for the Hook-Brown model. We do have a bunch of different creep models that allow you to do that. As far as I know, none of them are actually based on Hook-Brown. A couple of them are probably based on Moore-Coulomb. And then the second half of the question I'm reading in the Q&A here is, you could, in theory, take one of those models and modify it to work for Hook-Brown or add viscous elements to Hook-Brown. It would be a little effort, but you could probably do it. So,
and to clarify that second part that Jim was responding to, the question is, are there built-in options or supported user-defined models that allow you to introduce viscoplastic or strain hardening formulations? I'll just add that the plugin or add-on to do your own custom user-defined models used to be an option that was an additional cost, and we now include that for free as part of the base package. Okay, I'm not seeing any new questions, so Thank you very much for attending the webinar today. Recording will be posted to our YouTube channel. Thank you, Jim and Bruno, for your presentations this morning. It was very interesting, and I hope everyone has a great day. Take care. Bye-bye.
Thank you very much. Thank you all.